The only thing we can be sure of about the future is that it will be absolutely fantastic.
5, 4, 3, 2, 1.
Today, it's a great pleasure to be with you. Thank you so much for coming to meet me. We're at the campus of the beautiful Loyola Marymount University, located in the travel district of Los Angeles, not far from LAX, convenient to all major freeways. And it's a great pleasure to interview you. I've had the pleasure of reading your books for many years. I think you've autographed every copy I've had except for the most recent copy, because that I read an audiobook or listened to an audiobook. Do you have an opinion on audiobooks? Do you think you get as much out of an audiobook? Do you get more out of an audiobook?
I think
because you've read it. This one
you
read
get things out of an audiobook. You might not get the same things. I get, interestingly, there's a bunch of people who have written in to say that they get both. You know, they get the audiobook, and then if it's, because my books tend to involve, complicated things, right? Mind stretchy things. And then you want to go back to certain parts of the book and get it. So get both.
Get both.
That's the advice.
Get all three. Kindle, hard copy.
Yeah, absolutely.
Yeah, I know a lot of people.
Just for yourself.
A lot of people like
the
to read
triple play, we call that.
The Lagrangian at the end. That's the big picture. That was a standout. This latest book, your latest opus, I thought your previous book might be, used up all the words you could possibly use in your vast brain. But this one, even more, I think, deeply, truly does involve new ideas, new theories, new kind of modes of thinking about reality and the universe. And although, I remember when you mentioned it on Twitter, you're going to write a new book in the coming years. It was a couple of years ago. And you said, this book's going to be on quantum mechanics and it's going to solve everybody's problems. I'm sure everybody's going to understand
quantum mechanics after reading this. Yes.
And certainly we come away with a much better understanding of quantum mechanics. But I think the book is deeply misleading because it's really about gravity. And I felt that it was a very, very interesting and beautiful turn of events that only sort of partway through the book, after the requisite explanation of how quantum mechanics has been interpreted and could be interpreted, that you turn to a much more kind of exciting frontier, at least for physicists like myself and my colleagues. Of course, it's a popular book, but really, is this the book you set out intending to write 2 years ago when you made that famous momentous tweet?
The book has a very natural structure into three different parts. The first part is explaining quantum mechanics, the basics of it, and including a little light introduction to many worlds. And then the second part is a deep dive into many worlds, what it means, why it's difficult, what the alternatives are, etc. And the third part is, as you said, an exploration of gravity and the emergence of space-time, and an argument that one of the things holding us back from quantizing gravity is that we don't understand quantum mechanics very well. And in particular, the thinking about things in the many worlds way helps us quantize gravity. So I actually bounced back and forth when conceptualizing a book and when writing it. Should it be just about many worlds, or should it be many worlds building up to this particular view of quantum gravity? And literally with a very short period of time, actually literally after I had written the first draft of part 3, I said, let's take it out. Let's just stick with just many worlds, because it's a nice, compact, complete story just by that. It's a smaller book, more easily digestible, right? And my editor said, that he really liked the idea that we could show it in action in modern physics and research level stuff. He said, it's nice, but when all of your dates are 1960 or before, that's not as much fun as when some of the dates mentioned are 2016 and 2017 and 2018.
Right, and reference to modern results. But I think, really coming up with a way to hook the reader's natural curiosity about quantum mechanics. And there have been a plethora of books, no shortage of books, yes, as you point out, which is unusual because, that's for something that's not well understood. And I'm not going to use the famous line by the man who hold his desk, Richard Feynman at CalTech. You have the Feynman desk. Some professors are chaired, some are desks, some are. Yeah. But in this case, I think with all these books, and as you said in your famous, I'm sure everyone's going to understand my version of it. This is really the first one. I mean, there have been other books, but they tend to kind of have a concomitant description of the multiverse, and you get into it. But specifically with regard to Everettian theory, this is one of the more kind of notable ones that goes into the actual meat and potatoes of that theory. As I said before we sat down, I don't like podcasts where the host interviews the author. Says, tell us, what is a reader going to get out of your book? Because it means that the host did not read the book.
Right.
B, he or she is trying to undermine your sales, and I know you do that for your cat food budget. Although I want to point out that this is the first time, I think, in human history. In your last book, you quoted Bill and Ted, and that was excellent, no pun intended. In this book, you found a way actually to save Schrodinger's cat from ultimate annihilation.
No cats were harmed in any public experiment.
Hence the PETA endorsement on the back of the book. So I want to get a little bit outside the realm.
But let me just, on that note of what you just said, there are many books on quantum mechanics, and not every single one of them, but the vast majority have the philosophy that, isn't this weird? We'll never understand it. It's a mystery, right? And whether or not you believe many worlds, I wanted to undo that particular thing. That's why I did think that another book on quantum mechanics was something that had a place in the world, because I want to say, number one, it's not ineffably mysterious. It's just science, right? And number two, here's a possible way to make sense of it. Now, you might not believe my possible way to make sense of it, but it can be made sense of, and that's the more important message.
Yeah. I was questioning, whether or not, if I were in your position, would I advocate that a young, popular science author write a book about the foundations of quantum mechanics, as a means to, fund and profit? I'm not sure I would. And in the book, you point out the fact that nobody writes books about the interpretations of classical mechanics. I mean, you've touched very deeply on interpretations of statistical mechanics and the origin and error of time. In your previous books, the origin of Higgs boson, the particle of the universe, etc. But I think it's unusual because in our classes, we never sit down. We kind of get pulled a fast one. If you're a physics grad student or even an undergraduate, you don't need to know the foundations of Newtonian mechanics. As you point out, baseball is going to travel. We've all seen baseballs travel. And it's actually true that you probably should spend some time on the interpretations of quantum mechanics, the foundations of quantum mechanics, but we never do. We never teach it to our students that way. So I found this useful, for the professionals in the audience, that this is actually a useful tool for even, advanced or, first-year graduate students that are curious about quantum information, cubism, things like that, but also to understand what they're doing, because there's a Merman quote that you use often, shut up and calculate.
Which he was not saying.
No, I know he wasn't.
Right.
He just said, and calculate. Right, I think that's right. Yeah, that was sort of the intro. And I actually had the distinction of being told by none other than 2019 Nobel Prize laureate Jim Peebles to shut up and measure when I started asking him too many questions. He's the ultimate gentleman, of course. So he laughed at the colloquium and told me to shut up and measure the CMB. And that's what we're trying to do. And I think what's so interesting about this book and the connections that you make within it is this connection between the small things in the universe, the ultimate quantum things, and the larger things, the universe, which we study. And, to first order, it might be curious for the listener to hear why they should be related at all. I mean, why should the very smallest things be related to the very biggest things? That's maybe question, part one of a question. And part two is, how can, space-time itself, the framework in which Newtonian mechanics is played out upon, how can that emerge from quantum mechanics? And I think that's a key philosophical point you make in the book. And I think I think it'll be interesting to hear your thoughts on that. How do we get around this notion that this very small things have almost no impact? We don't have influence from ants unless you go in the basement and on the biggest parts of the universe. So what do you attribute this fascinating connection between the ultra small, maybe Planck scale structure of space-time and the grandness of the cosmos that we see today?
Yeah, I mean, I would say that quantum mechanics is not a theory of the very small. I think that sometimes we say that. I've said that. Everyone says that. But a more precise version of that statement is quantum mechanics becomes necessary when you think about the very small. When you think about the very large, when you get a rocket to the moon, you don't need quantum mechanics. You just do Newtonian gravity. You don't even need general relativity to get a rocket to the moon. So quantum mechanics is a theory that has a limit, which we call classical mechanics, right? In certain circumstances, under certain conditions, when things obey certain parameters, then classical mechanics is a very, very good approximation. But that's the puzzle, right? I mean, the puzzle isn't why we need quantum mechanics for the very small. The puzzle is why classical mechanics works at all, because classical mechanics is so different than quantum mechanics in a fundamental way. And this, I mean, part of the reason why I wrote the book is this is what I'm doing research on right now. Like, why is there a classical limit and where does it come from? And what you see when you do look at the literature on this is everyone cheats. Everyone knows the world is classical, so they just find the classical mechanics in there, but they don't show why it was necessary or how it could have been the other way. They take certain features of the world for granted, like the existence of space, right? Like three-dimensional space, up, down, left, right, forward, backward. They just put that in, right? And as you know, as a physicist, when you learn physics and you want to learn, okay, learning quantum mechanics, let's start with a harmonic oscillator. What do? They teach you the classical harmonic oscillator, and there's a process called quantization, right? Quantization. And again, nature doesn't do that. Nature doesn't start with some classical world and quantize it. And my strong conviction is that that's why we haven't quantized gravity, because we stubbornly insist on starting with a classical theory, whether it's general relativity or string theory or anything else, and quantizing it. And I think that if we just start with a quantum theory, a real purely quantum theory from the start without assuming any classical superstructure, we might be able to show how gravity emerges from it. But guess what? That's really hard. Yeah. Like, it's not at all clear how to make progress doing that. Well, one thing that is seemingly clear, but even there I'm going to hesitate, is the laws of physics need to be pretty special to get the classical world emerging at all. So why, or do the laws of physics have that property? I really don't know. I would like to know that. You know, in my more speculative moments, I wonder, like, is there, if you had a random, generic, truly unstructured set of laws of physics, could it somehow break up into different sectors, all of which had classical limits or something like that? But I don't really see how that could happen. So.
Yeah, it seems like, you know, this consistent, you know, fool's errand, which is, you know, to find gravity and have it be quantized. But to do it the other way around seems profitable, and of course you explore that in the third part of the book. And I think that is a unique, you know, not too often to my knowledge, I haven't seen that explored before. So to propose, you know, new modalities of thinking, I think is very commendable.
I mean, let's mention for the people who are not experts out there. You know, one of the things we talk about in classical mechanics is position and momentum, position and velocity. Right? Momentum classically is just the velocity times the mass of a particle. And that, in Newtonian physics, that's the state of a particle. You need a position, you need momentum, I can tell you what it's going to do. But clearly they're not on an equal footing, right? Like, the way that we teach it, the way we conceptualize it, position comes first, and momentum seems to be derived from that. But then you go to this more advanced supercharged version of classical mechanics called Hamiltonian mechanics, and the distinction becomes a little blurrier, right? Like, position and momentum now seem to be more equal. And in quantum mechanics, in the formalism of quantum mechanics, they're completely equal. You know, there's an operator P for momentum, there's an operator Q for position. One might ask why those are letters, but okay, they're the letters. Right. And all the equations, they appear symmetrically. And that really sort of begins to poke at you and say, why is it like that? Why is there a difference between position and momentum? So I have a chapter in the book about that, and I'm sure there's no other books that have chapters on that. That's right. For all you aspiring quantum mechanics, that's popular science. And I think, you know, even in my popular books, I want to say something substantive. I don't want to just say, here's the stuff we've discovered and present it pedagogically. That's part of it. But I also want to make an argument that people can potentially disagree with. That's one of my goals. I think also the fact that there's a frontier. It's not a dead subject. Yeah. It's not for, you know, people that lived 100 years ago. You know, I mean, it's been said by people. I think David Gross might have said, well, you know, we need interpretations of you know, or maybe he said something like this: you know, particles need particle physicists the same way that birds need ornithologists, you know. And I think Feynman again said something like that. Yes, that's right. So in this case, I mean, do we need it? I mean, as you said, classical Poisson brackets, Lagrangian theory, and then promoting it with quantum commutation relations. That's about all you get in Sakurai, or the, you know, classical text for those of you non-experts out there that we use in first-year graduate student classes. But nowhere in there does it say, well, there's a whole, you know, panoply of different ways you could interpret what is fundamental and what is the actual entity under which, you know, reality is to be ascribed. And I wonder, you know, in the many worlds interpretation, which obviously you're an advocate of, you've been an outspoken proponent of, you mentioned many times in the book how it's not only appealing to physicists, but it's also made its way into popular culture and films and so forth. You know, to what do you attribute the sort of
very dominant kind of, I have to be honest with you, it's almost like bias against the Everettian many worlds interpretation in favor of the standard, which every physicist in almost every book you have read and I have read will say, we know this isn't right, here's all the rules.
Yeah, that's right. Yeah, I think that, of course, most physicists, if you ask them about their favorite interpretation of quantum mechanics, they would just say they don't care, right? They don't even want to think about that.
Right.
And I think that's bizarre and weird. I mean, I've had professional physicists tell me, I don't care what actually happens in reality, all I care is what the measurement outcomes or the observational predictions. I don't think that any 12-year-old gets excited by science by saying, someday I'm going to make some observational predictions. So, like, I don't care what happens in reality. I think that you get excited because you're actually curious about the real world and what happens in it. And somehow we managed to beat that out of our students. So there's this thing called the Copenhagen Interpretation, which traces back probably to Heisenberg more than anyone else. And no one ever explicitly says what it is, and it's kind of very fuzzy, but it follows this idea that what we're supposed to do is just make predictions, not ask what's happening underneath the hood. And if you believe in the real world and there's something happening underneath the hood, I want to know what that is. So I don't think we should be satisfied with that. And I think that we should let our students not be satisfied with it.
Right. And yeah, we always have this image of the old ones, go into this field once their productive career has
once they're done with serious work.
Right, yeah. As you point out, Einstein, when he was thinking about spooky action at a distance, and EPR paradox was at the ripe old age of 48, which is my age right now. So I feel, I should have a more, kind of respectable beard and mustache and hairstyle. I want to talk about, some of the criticisms that the many world theory does have, but before we do that, because I think that's standard podcast, right? You probably haven't asked that one. I want to know more about you and what excites you, what fascinates you about life. I know that you are a very cultured man and you're a very erudite man. Obviously, your interests are highly peripatetic. They range from theology to deep in the heart of astrophysics, cosmology, fundamental physics. But I also know that you're an ordinary person. You are fascinated by many different things.
I know my pants one leg at a time.
One leg at a time.
Everybody else.
I've done it twice with 2 legs, but then I won't talk about that. I know you're interested in time. I know that you are an avid, have an avid fascination with watches, because I once watched you at an auction putting a $1,000 bid in a G-Shock. I found that very unusual, but to each his own. No, so I know that you're it was in a different world.
I do own a G-Shock.
You guys do I own a couple of them because they're not completely indestructible. You have a bunch of little kids around here. But outside physics, what is Sean Carroll up to? What kind of things do you do that make time pass by without you noticing it?
Yeah, I mean, I'm lucky enough that there are things that I do that other people might think are work, that I think are fun. Like I have my own podcast, right, called Mindscape.
Yes.
And I write books. And, it's interesting when you write books because I know many professional science writers. And that's what they do for a living, is write.
Yeah.
But they write articles for magazines or websites or whatever, and many of them hate writing books. And I hate writing articles, but I love writing books because I'm like, give me 100,000 words to set people straight, and that's really what I want, right? And one of the reasons why I started the podcast is because I love reading other people's books, but it's very hard to find the time, right? I had a big stack of books, and I'm never going to read these. But if I need to interview the author, then maybe I'll at least skim through it.
You're here today, and I finished your book.
And that's why, exactly. And that's why the podcast is very eclectic. I'm not like a thrill seeker in terms of skydiving or rock climbing like many of our friends are. I like eating good food, drinking good wine. We just got back from our annual vacation in Las Vegas where we eat an enormous amount of food. And I play poker, right? Yeah. Which is another kind of thing that is not surprising to hear physicists playing poker, right? Bayes' theorem comes up very, very often. But that's what I like to do. Read, write, talk to people, drink good food and wine. That's my life.
What about speaking and kind of the classical speaking versus debating versus being on podcasts? Some people, shy away from them. They don't like. They're more comfortable behind a computer screen or notepad. Where do you fall on that spectrum?
Yeah, I was, as a kid, one of these people who thought, debating was really fun. I joined the debate team, was on the speech team in high school. And I was terrible. Like in fact, like over and over again, I got the same comment that, what you're saying is somewhat interesting, but your delivery is sucks. It's just, you can't give a talk to save your life. And, I worked at it, and there was like a little phase transition. There's a moment I can pinpoint in my senior year in high school where I sort of became a good public speaker. And I loved being on the debate team because it did help teach you logic and argumentation and speech and so forth. But I actually don't like debating as such anymore. I mean, I think that
you have had some notable debates with people like William.
I've done it.
People that are vehemently, respectful, but
completely on the other side. I did one on life after death, for example. I do think that it serves a purpose. But, people on Twitter, for example, are like, debate me. I'm like, no, I think I love Twitter as a medium, but not for discussion. It's just for fun.
It's just pure, yeah.
But, debating, it's a performative act. I'm happy to debate with someone like William Lane Craig or Stephen Alexander, who I debate on Life After Death with, but not because we are advancing human knowledge, but because we're sharing some existing human knowledge with the audience, right? I think that if you actually, there's a different thing you do if you have two people with the same goals of understanding the world. They don't debate, they sit down and talk, right? They discuss, right? And that's much more like what I do on the podcast, right? Like even when I have people on the podcast who I disagree with, my goal is to let them have their say and maybe, note my reasons for not believing them, but then move on. Like I'm not there to show why they're wrong or anything like that. That just is not interest.
And a similar kind of canard leveled against science authors, popular science authors, is that it's not really something a serious scientist does. And, I got some criticism along those lines in my book, which you were kind enough to blurb with the phrase readable, which I thought was, a little overselling it. It was readable, but no, I think you were much more effusive in your praise, and I'm very grateful that you were so. But, kind of you get comments that, oh, well, you're spending your time writing books, and I'm in the laboratory during this, or I'm in the, in the throes of a calculation. So how do you react to that? How do you have the day job and the night job? And what do you view as the responsibility or maybe lack thereof of a professional scientist in terms of communicating?
I think it's not just scientists. I think academics more generally have this weird point of view that says, oh, you are spending your time making what we do for a living accessible and interesting to outsiders. Therefore, you are trash. Right. You are helping taxpayers fund me. Therefore, I disdain you. Right?
Yeah. Although they won't overtly say that, but that's sort of that's the functional end of their criticism.
I think that's exactly right. They won't overtly say it. But then when you say, well, what they'll say is, we love popularization or outreach or things like that. And then you say, okay, this person who does it, they're like, yeah, they're not that. It's not serious, right?
He or she can make it as a real
they should really spend their time doing research. So, what can I say? I spend my response to that is to not care. Like, just to do, it has hurt my career in various ways. It has helped my career in various other ways. So what can I say? It's what I want to do. So as long as I can do it, I'm going to do it, and they can live with it.
Right, and it brings you joy, right?
Yeah.
And I think that is
important. But you also mentioned about the responsibility aspect. I mean, I would be not completely honest if I said that I did this out of some sense of duty or obligation. I like it. I do enjoy it, and I enjoyed. Even if no one read it, I like the writing. Or like I said, I really do enjoy that sort of puzzle solving of getting the pieces together. And you learn things. You realize you understand things much better when you've written a book about that. I don't think that individual scientists have any responsibility to talk to the general public. I think the field has a responsibility. There's many scientists who I think would be terrible talking to the general public.
They should stay deeply hidden.
Fine.
They should stay deeply hidden.
That's perfectly fine. But I think that as a field, we rely on the public, and especially the kind of stuff that you and I do, which is not going to cure cancer, right? We're really in it for curiosity-driven research, understanding how the world works. And if the world, taxpayers and citizenry and the polity, comes up with money to pay for you to discover things about reality, and then you don't tell them what you discovered, like, what is the point of that?
Yeah, my late colleague, Hans Parr at UC San Diego used to tell me, we serve at the pleasure of politicians who currently aren't engaged in any serious war that requires physicists or astronomers to engage their mental capacities into, right? And that Neil deGrasse Tyson's written about that, the partnership alliance between astronomy and big military-industrial campaigns. I want to talk a little bit just about kind of the places that your mind has taken you, and I think a lot of as I see you in the role of a popular science writer, all of that's one of your many abilities, but also as a teacher. And I know that your teaching is very important to you at CalTech and in your kind of day job, so to speak, although I think you probably do it at night, or you think you write during the day or at Feynman's desk. But in terms of that axis of pleasure and obligation, I mean, where does teaching fall? Is it something that, one thing we're concerned about at the Arthur C. Clarke Center for Human Imagination is, can you teach imagination? Can you teach creativity? And as you know, and as I know, and many of our colleagues know, science is eminently creative. And I think to think of it as this purely analytic and quantitative aspect of human nature is not respecting its role as a part of culture. I think science is culture. And yet, some people, there is sort of a distinction between whether creativity, like, brilliance, can that be taught? And then where do you fall in that kind of axis?
Well, I think, something I've come to appreciate, that there was a weird thing that was said to me the very first time I taught my own course, which is when I was a postdoc, actually. Mm-hmm. One of the professors at MIT, where I was a postdoc, who was scheduled to teach general relativity, went on sabbatical and never came back. So they were stuck without anyone teaching the course. So they asked me as a postdoc to teach general relativity, and for better or for worse, I said yes. And that ended up turning into lecture notes, which ended up turning into a book. Right. So it's affected me in the world that way. But at the time, I was living, poor postdoc, living in someone's house. And I was living in the top floor of a house owned by this couple who were both psychologists. And the guy learns that I'm going to be teaching, and he was a professor himself of psychology, and he said, whatever the subject matter that you're teaching, what your students will actually take away from you, most importantly, is your moral example. And I'm like, maybe that's true when you're teaching psychology. Yeah, exactly. I'm teaching general relativity. Right. What they're going to take away from me are the symmetries of the Riemann tensor, right? But years later, I realized he was right. And maybe moral example isn't how a scientist would say it, but I don't know if you can teach brilliance or creativity or imagination, but what you can do is show it, right? I don't know how to articulate how to be a good scientist, but I can be an example of a good scientist. The way that you teach, are you willing to say, I don't know? Are you willing to do things in real time? How careful are you about doing different things? How interested are you in explaining why things are one way rather than the other way? How much do you care about how the students are doing, et cetera? All of that is at least probably much more important than the actual subject matter, which after all, they can get from the book.
Yeah, I mean, I've kind of noticed throughout the questions to many different experts, from Pulitzer Prize winning poets to Nobel Prize winning physicists, that there is sort of a notion that you can teach certainly well, and you can inspire, but potentially creativity has to be something else that's perhaps emergent once they're exposed to these things. It might be like some of my artist friends say, when I meet a young person who wants to be an artist, I say, go and paint the masters. First do that. First understand where it can, who are the masters in our discipline.
Learn the rules and then break them.
Yeah, that's exactly right. So I think that is kind of maybe holds true across this aspect of culture. And that same dear colleague of mine who passed away, unfortunately, last year, Hans Parr, used to say that general relativity was the crowning accomplishment of Western civilization. Now, I'll just leave that there. I want to add one other thing to what you said a few minutes ago when we were talking about taxpayers and so forth. Science, quantum mechanics, I would say, and astronomy in my case, is something that's apolitical, or it should be. I always say, there's no Republican constellation over there, Democrat comet over, it should be. And yet we see nowadays people wading into politics, and I think sometimes I think there's a little bit too much of the halo effect. This person, Albert Einstein, was very smart. He understood the speed of light, so let's ask him about, what should there be in terms of how many nations should there be on Earth. I noted that you have multiple online personalities, not in a bad way, not your psychologist ones, but you have a political Sean Carroll account. And do you believe there is an obligation for scientists to be political? And if so, is there some sort of scientific, litmus test or whatever that an authentic scientist should hold, or do you believe that you can have, sort of a full spectrum?
Yeah, I mean, I think that it's a little bit of an exaggeration to say that science is not political. The universe is not political. Right. The universe does what it does, whatever our political beliefs are. But science is a human activity that is embedded in politics and psychology and hopes and dreams and loves and fears, just like everything else, right? And admitting that, I think, is important. I think that there's no necessary connection between one's science and one's politics. I don't think that there's any responsibility on the part of individual scientists to get involved in politics. I don't think that being a scientist gets you any special expertise points when it comes to politics. But I also don't think that you should shut up about politics just because you're a scientist.
Sure. Yeah, no one.
And I think that, when I completely agree that, someone's a famous scientist, they're expounding on politics, there's no reason why the public should spend that much time listening to them, even if they're Albert Einstein. Likewise, if they're a movie star or a singer expounding about politics, and yet they do. But I kind of blame the audience for this, right? Like, let the movie star expound all they want. I'm not going to blame them for expounding. Right. But if CNN wants to report on their what is the noun form of an expounding?
Expose.
I don't know. Yeah, expostulations. And that's just crazy. Like, why should CNN do that?
And yet you see it quite frequently. Oh, there are so many Nobel Prize winners that are in favor of this treaty or should vote for that.
And there is sometimes there is an overlap, right? I mean, climate change is obviously a place for arms control might be a place where there's an overlap between scientific expertise and political expertise. And again, I think that scientists should be outspoken about politics if that's what they want to do, but they should be judged in how sensible their statements about politics are, not because they have a PhD in atomic physics.
Right. That's right. Any more so, people ask me to give a talk about cosmology, and then at the end, it's inevitable someone asks about climate change. And I always say, I hope when you have a talk about climate change and someone asks them about cosmology, they say, you should consult a real practicing cosmologist.
Like Rush Holt and Bill Foster, who are physicists who shifted into politics and did very well with that. So there's no incompatibility there, but there's no necessary connection.
So we talked a little bit about what you do outside of physics and outside the lab and writing. I want to get back into the book in just a bit. I do want to talk just more broadly speaking about your, as we say in the biz, world line. How you got to here today, maybe not here.
The 405
ways, that's right, which is more complicated than all of cosmology and quantum mechanics. But can you explain for the listeners who might not be familiar with your unique path to becoming atheist, I should say, or naturalist, as you say, for one example, and being a physicist? I believe that you weren't originally intending to be a physicist when you started off in college at Villanova. I thought, if I recall correctly, perhaps I'm wrong, but you had other intentions.
No, I definitely wanted to be a physicist.
Oh, you did? Okay.
I was one of these lucky kids who decided when they were 10 years old what they wanted to do. So I was reading books about the Big Bang and black holes. My favorite book was a completely unknown book simply entitled High Energy Physics. That talked about all these particles being created at the Bevatron in the 60s. So I was reading this in the late 70s. And I wanted to do that. I had no idea what that meant, to do that. And I even quickly figured out I wanted to be a theorist. I wanted to be a theoretical physicist, right?
Like 11.
No one wanted me in the lab. Like, I had a chemistry set.
I kept you out of the lab when you visited.
It's surprising that I kept all my toes and fingers.
I got the
chemistry set that I had. But I came from a long line of steelworkers and went to public school. No one in my family had any idea what this involved. So I got a full tuition scholarship to go to Villanova. And so I said yes, because it was free. So that was nice. And they had a very good astronomy department at Villanova. The physics part was not that great, but good enough that I could just do research. And, I got published papers out of my undergraduate research in astronomy. But I also got introduced to a lot of interesting topics in politics and philosophy and literature and things like that. So I became a philosophy minor. That became very interesting to me. And because a former Villanova alumnus was a research scientist at the Harvard Smithsonian Center for Astrophysics, I got rejected by the Harvard physics department, but the Harvard astronomy department took me. So that's why I stayed an astronomer, even though I'm not an astronomer. I'm not an astronomer. People out there are confused by this.
Constellations are not
an astronomer.
Right.
I collected data. I collected
That's right. Yes.
So I was in an astronomy department, but again, I got lucky enough to be matched with George Field as my advisor. And at the time, I mean, George is a super famous expert in the interstellar medium and galactic physics and things like that, magnetohydrodynamics, again, things that I don't do for a living. But he'd become curious about particle physics and cosmology. And so we wrote papers together and we learned together. And then I got lucky again because people at MIT, Eddie Party and Alan Guth, found me and asked me to work with them on general relativity and things like that, and hired me as a postdoc. At MIT, I went to the Institute for Theoretical Physics in Santa Barbara, met a lot of brilliant people like Billy Polchinski and so forth. I made, even though, you know, I should have left behind the fact that I came from a long line of steelworkers, like I never got either never got good advice or never followed it. Probably I got some good advice in there.
What kind of, give me an example of like advice you didn't follow?
Well, so just to set the stage for the non-expert, so I graduated with my PhD in 1993. So if you're on the cosmology side of things, that's right after we discovered the CMB anisotropies code, right? If you're on the particle physics side of things, or the particle theory side of things, that was just before we found dualities in supersymmetry and string theory.
So, gearing up to build the SSC.
That's right. But the point is, when I was in grad school, nothing interesting was happening in my field.
It was the desert, right?
So I was a hot property in the job market just on the basis of promise, right? 3 years later, when I was on the job market again, millions of interesting things were happening, and I wasn't doing any of them. So I was not a hot property in the job market anymore because people were either doing CMB or supersymmetric D-branes and things like that, string theory. And no one, no one explained to me that I couldn't just putter around doing whatever I wanted to do, even though no one else cared about it. So I made a huge mistake. Even when I moved to Santa Barbara for my second postdoc, I never wrote any papers with any of the faculty at Santa Barbara, which was just dumb.
Like from the network connectivity,
just from learning and learning new physics, right? Like I knew my little area of physics, but there's so much expertise and brilliance there, and I was like, I'm doing my thing, right? Now the universe saved me because I was like, by that point I was like, if I want to get a job as a physicist, I need to be the expert in something other people care about, right? But what am I an expert in? Not that many things. There was one thing I was an expert in that no one cared about, namely the accelerating universe, because they hadn't discovered it yet. But then in 1998, they discovered the accelerating universe. I had written a theory paper on models of dark energy. I'd written this well-known review article on the cosmological constant. I was best friends with people in both groups. Brian Schmidt, Adam Rees, Saul Perlmutter. I was someone who advised. I was mentioning the acknowledgments of the very first paper Saul wrote on supernovae with Ariel Gubar. And I collaborated with Brian Schmidt and Adam Rees and the group on the first paper on the equation of state. So suddenly, even though I didn't do anything, I was a hot property in the job market again, right? Like the universe changed so that what I did was interesting.
I mean, it didn't turn out. You were a professor at Chicago, right?
No, I got that professorship because the universe started accelerating. So that was discovered in 1998. I was hired in 1999.
Okay.
I was suddenly employable.
Now it came. It came. Finally, they said the acceleration of the universe isn't good for anything, but at least in that case, it turned out to do useful work to get you full employment. So I want to turn back a little bit to the book. As I said, I don't want to steal too much thunder from Something Deeply Hidden, wonderful new book published September 10th of this past year, and is a great Christmas present. It's been up for many awards, including Amazon's Best Science Book of the Year, and many other awards. Blurbs on the back from the most eminent folks in the fields of philosophy, physics, mathematics, astronomy, etc. So pick up your copies, plural. And speaking of contributions to GDP, some people estimate that quantum mechanics contributes 30 to 40% of world GDP if you consider all things like computers, the internet. As I said before, as we both kind of maybe hinted, maybe Feynman said it or Gross said it, does quantum mechanics need us to understand it? And in what place do the foundations of quantum mechanics are they important, or is it just to kind of establish your bona fides? You're a true physicists used to be called natural philosophers, and you've spoken about this in the past to the extent that physicists will utter the word philosopher. It's in utter disgust and derision. So how do we handle that?
Yeah, I think that you don't need to care about the foundations of quantum It's like if you want to calculate the scattering cross-section of electron-positron pairs, or if you want to build a better superconductor, or whatever, you don't need to care about the foundations of quantum mechanics. The only reason you need to care is if you care how nature works, if you're curious about it, right? Personally, I am curious about how nature works. Like when I'm not thinking about quantum mechanics, I'm thinking about what happened at the Big Bang, which is also not going to build a better smartphone or anything like that, right? But it is, there's a tiny fraction of us that have this enormous privilege that we're paid to think about the deepest mysteries of the universe. And philosophers are among them, right? Like there's not a bright line in between physics and philosophy. There's a strong overlap, a continuum between them. And I'm willing to take help wherever I can get, whether it's from physicists or mathematicians or philosophers or whatever, to try to understand the universe better.
So another interesting aspect of the book is that you talk a lot about the reality of the Everettian interpretation of many worlds and splitting the wave function. So maybe for the non-experts, if you could just delve a little bit into what does it mean to split the wave function? What are many worlds? Even though it is not, I would say it's not the core aspect of the book, and that, I mean, it's an important part of it. It takes up most of the first two sections, but still, it's not the ultimate conclusion. I think a lot of the conclusion depends on it, obviously. But can you first say a few words about what are many worlds? What is the many worlds interpretation, and maybe explain what is an interpretation?
Yeah, so it's not an interpretation, by the way. I mean, It's been called that. Everyone calls it that. I call it that.
It's a shorthand.
It's a theory. Like what we're dealing with now, like maybe back in the 1960s, we were debating different interpretations of quantum mechanics. But as I say in the book, like it's not debating interpretations of War and Peace or doublets, right? It's a different scientific theories with different variables, different experimental predictions in many cases. And many worlds is one of these theories. And the idea is simply every version of quantum mechanics says an electron can be in a superposition of spin up and spin down, right? And when you measure it, it's either spin up or spin down. But when you're not measuring it, it's both. It can be a combination of both. And Hugh Everett, who was a grad student in the 1950s who invented this theory, said, well, look, you're made of electrons and also protons, neutrons, but you're made of particles which you certainly believe obey the rules of quantum mechanics. And as we started the podcast with, everything should obey the rules of quantum mechanics, so you should obey the rules of quantum mechanics. So let's not do the Copenhagen thing, which is treat you as classical and imagine that you look at the electron. Let's treat you as quantum mechanical also. So that's a sort of move that he makes, which if it didn't lead down a certain road, everyone would be happy with, right? But,
and Wheeler did approach that question even before Everett, isn't it? If I recall correctly. I mean, he was interested in the wave function of the universe.
Everett's thesis topic was quantized gravity. But he realized, that no one stands outside the universe to observe it, so I need to do a little bit better. But anyway, he said, look, if you obey the rules of quantum mechanics, then you can be in a superposition. So let's ask what the Schrodinger equation, the fundamental dynamical equation of quantum mechanics, let's ask what it predicts when you measure this electron. And again, everyone agrees on the answer to that question. The system, U plus electron, evolves into a superposition of the electron will spin up and you saw it spin up, plus the electron will spin down and you saw it spin down. And Everett's brilliant second move was to say, and that's okay. It's more therapeutic than physicists. He's like, just believe that. Don't bend over backwards to deny the reality. This is what the equation says. What if that were just true? And he argues if it were just true, we would interpret that as two separate worlds, because what happens in that one part of the wave function and the other part, once they're created, they have nothing to do with each other. Nothing that happens in one part of the wave function ever affects the other part. So it's as if they are completely different copies of reality. So the point of many worlds is that he never put in a bunch of worlds. The worlds were always there. All he did was say, let's accept that the worlds are there, ask whether or not people living in those worlds would see the kind of world we see, the kind of events we see. And he says, yes.
To be fair, that is an interpretation. I mean, that's sort of an interpretation, right? I mean, you're saying, let's assume it's okay, sort of giving the imprimatur that it's okay to treat them for the purposes of this exercise, right? For now, we have not actually come up with a to this point in this particular question. We have not come out with something specific that is an experimental test of the many worlds, or something that you would observe differently were many worlds to be accurate description of reality.
Well, it's a theory because it's a set of mathematical structures that evolves in a certain way. Now, that's just like classical mechanics or general relativity or whatever. And of course, you have to point to things in the world and say, this is what is being represented by that mathematical structure. You have to do that in any theory. And Everett has a way of doing that that is more problematic than classical mechanics, where everything is pretty straightforward. So that's fine, and we can argue about that. But it's eminently falsifiable, because all Everett says is there are wave functions and they obey the Schrodinger equation. All you need to show me is a wave function, either a wave function not obeying the Schrodinger equation, or something in the world that is not a wave function. If you do either one of those things, you have falsified many worlds interpretation.
But won't those apply to the Copenhagen interpretation too? Which says
who knows what the Copenhagen interpretation is? I mean, Copenhagen certainly says that quantum systems do not obey the Schrodinger equation when the wave function is correct.
Sure.
And Everett says they always
smooth and uniform behavior, and then collapse in this violent sort of event. Right. Okay. So for somebody that did want to, as you talk about in the book, in a very cute conversation between the daughter physicist and the father philosopher, maybe a daughter, she talks to her father and says, imagine you're a billionaire llama. And I'm interested in both, because, my experiment right now, the Simons Observatory, is in Chile. There's no shortage of llamas that we could eventually obtain, and there's a shortage of billionaires.
Right. I mean, maybe one of these llamas wants to win.
So you're a billionaire llama. And I want to know, how would you go about actually creating a test that you could endow, the Carroll Institute of Technology or the Simons Observatory? We're accepting donations. It's the season. What kind of experiment could you do? It's unlimited resources.
People are doing it. It's not a thought experiment. People are doing this experiment. Get a bunch of atoms together, cool them down, so it's like a Bose-Einstein condensate or so forth. There are theories in which, very explicitly, the wave function undergoes spontaneous without anyone looking at it, without the Schrodinger. So it's a explicit violation of the Schrodinger equation. And you can calculate that basically dumps energy into the system. So it will ruin the Bose-Einstein-ness of it, right? The fact that it's a condensate, right? So it's very rare for any one particle to undergo one of these transitions, but if you get enough particles together, it will eventually happen. So like the rate per particle is something like once per 300 million years. So you need a bunch of particles. So it's not an easy experiment to do, but it's a very clear signal that would rule out many worlds.
How close would you say we are to that type of, and it does, I want to take one other step back. Previously, you and I have spoken about Karl Popper and the things, demarcation, supposition that Popper suggested that something is not scientific if it cannot be falsified. And you and I have talked about this, and his original targets, and you discuss a little bit in the book as well, were things like Marxist dialectic materialism. And I always point out there's a lot more Marxist dictatorships on Earth today than in Popper's time, so even he's been falsified. But physicists take that as sort of a sacrosanct, law of nature. I personally think that owes to a deep sort of envy, a philosophical envy of the Gödel's incompleteness theorem in mathematics, which says that you can't make sure that a formal system of mathematics is self-consistent. And so to obtain a parallel structure in physics, we kind of rely on this Popper's definition, and it leads people to say some pretty hostile things, not about you, but to say things about like the multiverse and even many worlds that it is not it's not scientific because it cannot be falsified. Now you're talking about a falsification, and due respect to my experimental colleagues who make Bose-Einstein condensates all over San Diego, my laboratory is not the coldest part of San Diego. It's pretty close, but 6 millikelvin currently. But they can get a lot colder. So why have when will this occur? I mean, we've had Bose-Einstein condensates for 30 years now, 40 years or more. So what are some of the practical impediments behind this? Is it a matter of time? I mean, are there things that come into the wave function splitting, the time scales for that? You mentioned 300 million years. What kinds of things could we do to accelerate the discovery pace?
Yes, let me just mention parenthetically, we already agreed that listening to physicists expound about politics shouldn't give them any more credit than a person on the street. Likewise for philosophers, right? Likewise for physicists expounding about philosophy. Physicists love to think that with 15 minutes of thought they can solve all the philosophy problems in the world. Right. That's not true. So when you listen to physicists or other scientists talk about the scientific method or what is or is not science, just, it's a free country. They can go ahead and do that, but they have no expertise whatsoever in that particular question. But even if you take Popper at face value, many worlds is perfectly falsifiable for exactly these reasons. And Popper said good things about many worlds. And I have to footnote, he didn't agree with it. He didn't like it, right? He said it was much better than Copenhagen, which was a monstrosity.
He also
right?
liked the steady state universe. Right?
He had his own weird interpretation of quantum mechanics.
Not that prevents
not a physicist, right? But he thought that many worlds was fine, in terms of philosophy, and it is very falsifiable. Now, this example of getting Bose-Einstein condensate and looking for spontaneous collapses is an unusual one just because it's so good. It's like so crystal clear. If you found this, it would be ruled out. There are other alternatives to many worlds, such as Bohmian mechanics, which is much harder to see how to rule them out. In fact, there's plenty of people who believe that they cannot be ruled out, that they're experimentally indistinguishable from many worlds. I'm not so sure about that. I think that this is part of the ramifications of the fact that we haven't taken the foundations of quantum mechanics seriously. So people haven't really thought as hard as they can about these questions.
It's interesting to see now. I have colleagues at UC San Diego, and Dr. Andrew Friedman, and Dan Kaiser, and Owen Guth that are working with me and others on so-called cosmic bell tests. And some of these have, really ruled out as many loopholes or the phase space of available loopholes that could plausibly explain using invariance. So, it does seem there is a resurgence, and they're not the only one. Chinese groups are very, the National Academy, very interested in this type of work, quantum information. Maybe we're at the, precipice of a revolution when these types of experiments will be taken, with the seriousness that perhaps they deserve. So I think it is interesting to note that this is something that is potentially falsifiable. And it sounds like you're willing to grant falsifiability as having some measure or contributing to a metric of success of a theory. Maybe not the definitive one, as Popper might have argued.
Well, I think it's sufficient but not necessary.
Right. Okay.
If you can say that it's falsifiable, then what's your complaint, right? I mean, here's how to falsify it.
Right. One thing I took away from the big picture, your previous book, is sort of this contention that only that which can interact with the core theory and is real or can be considered real. So therefore, poltergeists, and astrology, and maybe even God and things like that cannot be, there's no God particle, despite Liam Letterman's terminology for it.
So a lot of books with that terminology.
That's right.
I don't blame him.
Yeah, it's like gotta move your books.
Yep.
But the question of whether or not these many worlds, I mean, is there an interaction with the core theory? I mean, can you overlay the superstructure of many worlds itself and ask, does it interact with the core theory, or can it? And so you might want to explain what is the core theory, Frank Wilczek's definition for what if you maybe explain what that is first.
Yeah, I mean, just to answer the question, of course they do interact. I mean, they split. They came from the same place, right? We share the same past. The worlds came from the same place. There's a very physical, tangible interaction between them in the past, just not in the future, right? So the core theory is this way of thinking about the laws of physics that govern our everyday lives. And that's a very expansive definition of our everyday lives to basically include almost every experiment ever done here on Earth, right? So the idea that the world is a bundle of quantum fields describing electrons and quarks and neutrinos and so forth, interacting through the rules of quantum field theory and the forces of nature, electromagnetism, the strong force, and even gravity at the quantum level is included here, because as long as you're within a weak gravitational field, far away from black holes or the Big Bang or whatever, we understand quantum gravity fine. So literally everything you've ever seen with your eyes, touched with your fingers, etc., is well described by this core theory. And people continually misunderstand what I say in the book. I don't think you do, but other people do. So I'll say it out loud. They think what I'm saying is that this existence of this core theory either proves that God doesn't exist, or proves that life after death doesn't exist, or proves that telepathy doesn't exist. But none of that is right. What it proves is that if you want to believe in any of these things, that somehow affect the world in a way that would show up in your everyday life, then you're saying that this core theory, which I give the equation for in the end of the book, you can buy a t-shirt with the equation on it, you're saying that's wrong. Right. You're saying it has to be modified in some way.
It's insufficient.
So this theory has been tested 6 ways from Sunday, so if you're going to say it's wrong, fine. Tell me how it's wrong. Tell me exactly where it goes wrong. Forget about God and all that stuff. If you think that consciousness is something other than a manifestation of physical stuff, tell me where this equation goes wrong. That's your burden, because we've established that the equation is pretty good.
And could one not say, well, in the future, just as we didn't know about the weak force, and the core theory of 1929 is very different than the core theory of 1939, et cetera. So are you just thinking historically? Could one say, well, we don't know how the soul part, the solon or whatever, the crouton, interacts with the core theory now, but you're shortchanging experimentalists of the future? Could one not say that? And
one cannot say that. That's the thing, because it's a special feature of quantum field theory. There's different ways of talking about it, but in the book I explain this idea of crossing symmetry, that if something can affect an electron in some way, then you can rotate by 90 degrees, and you can make that thing by smashing electrons together, right? Fields that talk to each other and have an influence on each other can be created or destroyed by each other. So if there were things that affected the quantum fields of the core theory, we could make them. They either are just not there, or they interact so weakly they have zero effect on our everyday life. And no discoveries in future physics will change that, unless those discoveries say quantum field theory is entirely wrong.
what about in the other direction? So obviously the soul is something human-centered, would have to be a low-energy phenomenon. What about those who say, well, we haven't reached high enough energy? When you reach 10 to the 16 GeV, looking at the early quantum universe, perhaps today, you might see evidence of some particles. What about the other end?
That's not our everyday life. Yeah, so outside our everyday life, in the very, very early universe, of course, the core theory is nowhere near sufficient.
In one of your talks, I think it was at Oxford on the philosophy of theology, you have a talk called God is not a good theory.
Right.
Not God is not a theory, but God is not a good theory.
They misprinted the title, actually.
Yeah.
So I've joked about that.
And in the talk, that's true. And in that talk, you give a few different arguments, and one of them, which I took issue with, was the notion of, you show the Hubble deep field. You say, what's the point of all these galaxies if there is a creator? So I wonder if you can maybe recapitulate that argument. But I could say, well, there's 116 elements on the periodic table, and maybe God's advocate in this case would say, well, what is the purpose of any of those? Why do we need them? We're only made of, maybe 36 different elements in the body. So aren't you being too, anthropocentric when you talk about what's the purpose of these galaxies? Who knows? I mean, what is so? As an argument against the existence of God as a good theory, not existence of God itself, but why is that sort of a persuasive argument in your opinion?
Well, because good theories make good predictions, and we're thinking about this as good Bayesians. Okay, so we have different theories of the universe. There might be theistic models, atheistic models, whatever, and then little subcategories within there. And then you ask yourself, the whole job of testing theories is you say, if this theory were true, what should I observe? And then you update. You have a prior probability for all of your theories, and you update that to say, depending on the likelihood of would you have observed that. So if all you knew was that God created the universe and God loves us and God has some special place for us in his heart, what do you predict should be the large-scale features of the universe? Well, we've done that experiment because there were people thousands of years ago who had this belief, and none of them predicted 200 billion galaxies spread uniformly throughout the world with no human beings on them, right? It's completely irrelevant to us. If all you needed was to make humankind, there's much easier ways to do that than to create all these universes. So either, let me just finish. So either you say, well, I have no idea what God predicts, or you say, well, God wouldn't have predicted that, therefore I lower the probability. And if you say, I have no idea what God predicts, you're saying God's not a good theory.
Right. Okay. Yeah. So I would say just the same. It might be, to paraphrase what you're saying, the existence of the extra 108 elements or whatever on the periodic table is further justification in a maybe perhaps parsimonious God. But, to use a trivial case, I have, 8 colleagues in San Diego who study the Hubble Deep Field, who study every one of those galaxies. And, it might be, again, God's advocate. The purpose of those galaxies, is for human curiosity to understand the universe. Again, I think when you overlay on top of it the notion that, these attributes of God, that's another thing. But, perhaps it's, again, just speaking, trying to summarize, the excess of these elements and things that we can't interact with or see no purpose for, it's not clear to me that entirely invalidates the notion of even a personal God, but certainly taking away the personal aspect of a God entirely, a God, a creator that created the universe, perhaps. I don't know that necessarily invalidates it, right? Because it's just a trivial example.
I want to say, come on. I mean, of course, you can, after the fact, invent some ex post facto justification for, God would have wanted to do exactly that. And this is the entire history of theology, discovering new facts about the universe and go, that's just how God would have wanted to do it. And never did they say ahead of time, God will want it to be this way, this way, we're going to predict it. That's why it's a crappy theory.
Okay, good. So I want to conclude in the last few minutes with the plug zone. I want to go and refer people, and I will. I'll put a bunch of links to that talk that we just mentioned. I want to put links to the book. Any other things that are coming up in Sean Carroll's universe that you'd like the audience to know?
No. I mean, subscribe to the podcast, but it's the usual thing where after the book comes out, Mindscape podcast. After a book comes out, then it's back to science for me. So, like, I'm feeling very chagrined because this is a very low publication year for me because I got the book out and everything, and I have like 3 or 4 publications that are within Epsilon being written.
Top 10 bestseller. Another one.
But I want to get these papers done. So, if there are any physicists out there, by all means, look for papers. I have papers coming out on quantum mechanics, cosmology, and one that I'm really very excited about statistical mechanics and causality. Why the past, why you have causal influence over the future, but not the past, right? Relating to sort of J.F. Pearl's ideas about causality and things like that. So it's something that people have mumbled about, but I think we can make it a bit more rigorous.
Okay, last question. Dream guest for the podcast.
Alive? People who are alive today? Do I get to ask Galileo?
You can't violate the core theory, Sean.
All right. People who are alive. I've been asked this before, and I've never given a satisfactory answer, and part of it is I've done pretty well with getting my dream guests, and I have a few more coming up who are pretty good, I have a long list of people who I have not invited, but if I did invite them, they might say yes. So, I'd love to have Martha Nussbaum on the podcast. I'd love to have Barack Obama on the podcast, actually. I have a rule against current politicians or candidates because I think that they have a vested interest in trying to get elected, not telling the truth, right? And Obama probably also has that, even though he's out of office, so he probably wouldn't count either. But
he'll have you on his Netflix special.
Yeah, and all these people, recently passed away. Noam Chomsky would be a good guy to have on the podcast. David Deutsch.
One with Jennifer.
David Deutsch, I do want to have.
One with Jennifer.
Jennifer doesn't want to do it. She doesn't want to. She likes writing. She just wants to stay. She's the equivalent of a physicist. She wants to stay home. She wants to be a
we had her down for a Math for America speech.
You can coax her into doing it, but she's much happier at home with the cats writing.
That's great. Let me show you the book one more time out there in Hilbert space. Hilbert space is real or not?
Totally real.
Okay.
Well, the universe is real and it's an element of Hilbert space.
Get the book. Audio, visual, Kindle, any form possible. Something Deeply Hidden by Dr. Sean Carroll, physicist at California Institute of Technology. Thank you, Sean.
All right. Thanks, Brian.
The only thing we can be sure of about the future is that it will be absolutely fantastic.
5, 4, 3, 2, 1.